Hello viewers, welcome to my channel. Um, I'm Muhammad Naushad Arslan Islam. I'm a doctoral research assistant at the University of Texas El Paso. Today I will be giving a presentation on one of the projects I worked for my computational mechanics class. It's a finite element simulation of an additive manufactured injector at high pressure, high temperature environment. This is basically a work also I do as my research for my doctoral degree. So for the outline today, I'll be giving you a brief introduction, a motivation behind this work, backgrounds, objectives for this work, geometry that we used for this work, the boundary conditions that we used, mesh optimization that we did for figuring out a good mesh for this work, and we'll be discussing about the results, and finally we'll conclude with the decision. So additive manufacturing, as a lot of you guys know, is a unique layer by layer manufacturing process that basically does is it manufactures the part by adding materials instead of removing materials by old uh, compared to the old conventional designs. So what it gives us a lot of freedom to actually um, make complex shapes, complex cats for this for the parts because you're adding materials and not removing it. So basically, when you're adding materials, you can basically do different type of complex designs, and you can basically make the part without much of a hassle. But so also it also opens up a new era for allowing smart parts fabrication. That is basically you can embed sensors into the part, and yeah, you can basically now look into real-time scenario of a gas turbine inside a jet engine, or the gas turbine blade inside a gas turbine or jet engine or steam turbines. And basically now engineers are having more and more visual uh, visualizations into the high pressure, temperature, harsh environments like combustion, propulsion, and extreme and hazardous environments. So the motivation behind this work was that if when you're additively manufacturing a part, you can basically make a part really fast compared to the conventional machinings. When you're additively manufacturing a part, it basically takes you like around 2 days to manufacture an injector using powder bed fusion technology, where for an injector by machining it'll take you around 2 to 3 weeks, even months. Also, you cannot make a very complex injector due to the constraints of machining process. So for this project, we were going to look into a powder bed SLM fabricated additive manufacturing injector, which is basically one of the powder bed fusion technology. This basically what does is that it actually melts a pool of powder by selectively using laser on it, and it deposits that powder into a build plate, and it and it goes in cycle until the whole part is built. Um, so um, to achieve this goal, we wanted to look into a design of an injector that is already in operation, but we wanted to see if it could hold up to high pressure and high temperature environments of a supercritical oxyfuel cycle, and if we would need to basically remodify it for operating at an even higher pressure. So the best way to do it is do a finite element analysis on that part, and we can figure out how well it is designed and how much temperature and pressure it can withstand. So The results of the simulation would basically give us new insight for uh, taking into consideration for new designs, whether we need to reinforce the design, whether we need to change the design, whether we need to uh, design for cooling channels or not, or heat transfer equipments inside the injector, uh, or whether if we have to completely do a new design for this injector. So that's basically the motivation for this project. Um, so let's go into the backgrounds. Why are we doing this? So in 2019, 63% of the total energy production in United States have come from fossil fuel. So that means a lot of CO2 emission. Um, if we look into the statistics, we can see like in 2017 we had like around 6,500 million metric tons of CO2 emissioned by uh, different energy systems in the US. Of those, almost 5,700 million metric tons of CO2 emission was not sequestrated. So this basically went into our atmosphere. Um, US basically accounts for 82% CO2 emission worldwide. So that's really, really high. Now, to for remedy of this, engineers and scientists have looked in for newer ways to sequestrate CO2 and for green energy. Um, One of the best way to do is using an oxy-fuel supercritical cycle, which is going to be a next generation on the power production technology. So in the future, all of our power plants are gonna go oxy-fuel supercritical cycle. This basically means that what it happens is you combust at a really high pressure that actually allows you for higher efficiency, and what it helps is it actually increases the pressure on your CO2 film in the exhaust, so it makes it easier for CO2 sequestration when you're sequestrating it. As you all know that um, for oxy-fuel supercritical cycle, there's a bar on the technology that the CO2, the compressor takes in a lot of the energy produced, and it actually reduces your um, overall net efficiency on the existing thermal power plants if you're going to do a CO2 sequestration on it. But when you're actually looking into the oxy-fuel supercritical cycle, is because you're increasing the CO2 pressure and the film pressure, you actually end up um, and, increasing the efficiency as well. So that's basically good for us. We can get green energy as well as higher efficiency output, so lower cost of electricity. There have been different researchers who worked on this field. McClung et al. McClung was one of the very first persons who worked on this uh, very broadly, and he used a supercritical combustion cycle with a Brayton cycle, and he saw that it can achieve up to 64% of thermal efficiency and give a 52% net efficiency after the sequestration. Um, the cycles, according to him, goes up to around 29 megapascal or 20 uh, or 290 bar. So that's really high pressure, and temperatures can go up to around 1500 Kelvin. Um, Another researcher named OG, he found out that the CO2 and the CO2 from supercritical cycle reduces carbon dioxide pollutant by 10% and operation cost by 20%. He also found out that the thermal efficiency increases by 14% as well. There has been different works going on, and a lot of these works have been funded by DOE. So from DOE's different workshops, we got to know that these cycles they can actually achieve up to 99% of carbon dioxide uh, capture. That is like really, really green energy. Now, the current prototype that we have in CSM, the high pressure combustor, that can achieve up to around 100 bar of pressure, design pressure. And the recent test on it by Arifu et al. Saw it about going to up to 18 bar of pressure. So that's where we're gonna start our research, like going from around 16 bar to 100 bar, whether this new injector can survive or not. So the objectives are for this project is that we're going to need to investigate a structural analysis up to 100 bar to see if it can withstand the pressure and the stresses. The failure criteria would be any plastic deformation. So if it undergoes yielding, then it'll fail. The other thing that we'll look into is the material temperature increase due to heat conduction. Now, if the material temperature increases beyond melting point, or if it increases too high, we know that with increased increment of temperature, the yielding point goes down, so it'll deform plastically faster. So we need to look into that as well, and also make design consideration based on these two outputs to see if we need to design a new injector or we can work with this injector by doing some modifications. The geometry, as I already told you, that is already existing. This is an SLM fabricated coaxial shear injector that we're working on right now. You can see the CAD on your right for the injector. It basically has four fuel inlets and four oxidizer inlets. So you can see the smaller ones on the larger the larger holes are for the oxidizer inlets, and the smaller ones that's coming out of it are the fuel inlets. Now, this injector has a capacity of around 500 kilowatts of firing input. It also has integrated thermal temperature sensing capacity from at the injector face, so we basically know what temperature is facing during combustion at supercritical cycle. Uh, the material used for this ejector is Inconel 718. The density is about 8,000 kg per meter cube with Young's modulus of 200 gigapascal, yield strength of 980 megapascal, Poisson's ratio of 0.294, and thermal conductivity of 11.4 watt per meter Kelvin. All the structural properties have been experimentally obtained at the WM Keck Center for 3D Innovation at UTEP during the fabrication of this injector. But you could also look up for the commercial Inconel 718 properties from different manufacturers as well. I got the thermal conductivity from the specialmetals.com. They're a manufacturer for Inconel, but the density, Young's modulus, yield strength, and Poisson's ratio, they're basically taken from Keck Center. So this is the geometry. I redesigned it in Design Modeler in ANSYS, and you can there's interesting thing that you can look into. I've taken a symmetry of this because I wanted the computational time to be less for doing this project. And you can look into, there's, if you look into inside of this oxidizer lines, you can see like there are basically support structures that are holding these field lines inside. So these are basically the only structures that holds these field lines in place. So sustainability of these structures are really, really critical. So we have to have these structures sustained at higher pressure as well. So we go into the engineering data and we've put into the kernel 718 properties for using it in ANSYS mechanical. The boundary conditions that we used in ANSYS mechanical for this project are there. There's fixed supports on the flange of the injector. All the bolted connection are considered as fixed support. Also, due to symmetry, I have given a frictional support on the along the symmetric plane uh, on the injector, and I've also added displacement on the injector's outer side of the injector body because it's gonna be going through uh, slotted compartment into into the combustor, and basically on that compartment it's not free to move at any direction. So I've given a 0 mm displacement at all direction. We could also go with a fixed support on that as well, but I decided on giving it fixed displacement. Uh, Excuse me, a loading criteria um, from about atmospheric to 10 megapascal at atmospheric to 10 megapascal during a transient simulation. So the thermal boundary conditions. For thermal boundary conditions, we've decided the initial temperature to be atmospheric at 22 degrees Celsius. We've also assumed there's constant heat, temperature surfaces that are going to be at 22 degrees Celsius. These are based on experimental results because these lines always keep on um, operating on fuel or high pressure nitrogen during combustion or high pressure argon. So that actually allows these surfaces to be at around atmospheric uh, temperature instead of getting hot. So we've allowed this surfaces to be at atmospheric temperature as well, a constant temperature of 22 degrees Celsius. Also the flange, because it's a 15-second test of the heat conduction through the uh, bulk combustor to the flange is not that much fast for the flange to see that amount of heat. And due to the purges going on around the injector, the temperature does not increase on the flange. For um, for thermal input, we also gave heat flux on the injector face, the bottom face of the injector. That's basically where it actually sees the combustion. You can see on your right changing heat flux for um, different firing for selected firing input at different times during a transient combustion, transient simulation. So the transient solution settings that I used for structural and thermal are basically similar. So for the analysis settings, I assumed it's one, this number of steps are going to be one, but the step in time would be 15 seconds, and the steps would be defined by time. The initial time is gonna be like around 5 milliseconds, initial starting time, and the minimum step time would be 5 milliseconds as well. Um, Excuse me. Sorry. Initial step time would be 50 milliseconds, and minimum step time would be 50 milliseconds, where maximum step time would be 1 second. Um, for the loading conditions for structural, we went up to 16, 20, 25, 30, 40, 50, and 100 mega 100. I'm sorry, that's a typo. It's going to be a bar, so that will actually be 1.6 megapascal all the way to 10 megapascal. The firing inputs are going to be 250, 300, 350, 400, and 500 kilowatts, which actually results into the heat flux showed on the right around 5 milliwatts per millimeter square to all the way to 30 milliwatt per millimeter square. We've performed coupled static structural and steady thermal simulations and uncoupled transient structural and transient thermal simulations because uh, um, it was basically um, computationally inexpensive, and um, it was within my range to do in a commercial laptop. Um, Also, one of the reasons I did uncoupled because there was no thermal stresses involved because the injector could deform on the z-axis freely due to thermal expansion. So there was not much of thermal stresses involved. So that's why I intended to do uncoupled on the transient one. So let's look into the mesh. The mesh I used is triangular mesh with a body sizing of 1.5 millimeter of element. I kept the physical reference, the relevance to be 0, the center relevance to be fine, the span angle center to be fine for finer meshes, and I ended up with around 450,000 elements for this simulation. You can see the elements over there. You can see it's completely uniformly distributed all over the injector. So now the mesh optimization I did, I looked into both triangular and hex-dominant mesh. I tried doing multi-zone mesh, but it doesn't take into the multi-zone. The multi-zone mesh does not work very well with this injector design because of all these curves and other stuffs, other features. But So we're gonna take into proximity and curvature into account, and we did body sizing of the injector using triangular and hex dominant, and we varied element size from 4 to 1 millimeter at different intervals. You can see the mesh optimization results. You can see the total deformation. It basically did not change that much with number of elements. Also on the uh, stresses, you can also see with number of elements the stress tends to go up higher. The result is due to a stress singularity. So I figured out that we have a stress concentration zone, and the lower you go on element size, the stress starts to increase because it's a stress concentration point, and it gives you a stress singularity problem. So where your basically stress keeps on increasing with your decrease in element size. So we looked into the static stress error, and we figured out that the maximum error was in the order of 10 to the negative 3 for all the cases. So that's basically very low. And also the maximum error was basically on the structural the stress concentration zones. So we figured out that the element size of 1.5 millimeter with 400,000 elements should be fine for us for a good result, and it'll be computationally inexpensive. So let's go to the results and discussion. This is a typo. It's a von Mises stress, not a maximum principal stress. So this is a von Mises stress that we're looking into. Um, so so the von Mises stress is in this case is for 16 bar. So if you look into the stress case, you can see like the stress is reasonably resolved on all over the injector, except the injector face. So the stress is reasonably lower everywhere else. On the injector phase, the stress is around, the average stress is around 15 to megapascal, and you can see around the edge of the injector, their stresses are around at 20 megapascal. And the highest stress is 35 megapascal, which is basically at a stress concentration region. So we're not very concerned about the stress concentration, but if you look into overall stress, the stress is the reasonably low on the injector phase during 16 bar. So if you look into 50 bar and 100 bar conditions, you can also see the similar kind of actually stresses pertain in a similar fashion, but the maximum we've seen is around 222 megapascal of pressure, of stress on a stress concentration zone, where the median is about 130 megapascal. So that is basically really low compared to the yielding stress of 980 megapascal of Inconel 718. So basically, there's not much deformation or not much stresses going on into the injector for us to be concerned. Also, if you look into the support structures inside, you can see that there's not much stresses involved in there. So basically, we're doing good for the structural part when considering stress. Now, this is a plot for maximum principal stress at 100 bar. So we wanted to look into also maximum principal stress at 100 bar if that is higher, and we saw that it's higher at about 300 megapascal. Now, if when we look into it, we could see that it is actually occurring at the outer edge of the bottom injector face. So it's basically due to the constraints of the supports and the pressure from the combustion. Now, but if you look into the median value of the principal stress, that's basically lower than the von Mises stress and is way lower than our yielding stress. So we're basically doing good with this design for the structure part. Now, if we look into the total deformation, we can see we have like around 0.054 millimeters of deformation on the fill wall. Now, this deformation is very insignificant um, based on compared to the whole injector's dimensions. Um, Also, we've seen like not a very significant deformation on the injector face, so we're doing good on the injector face as well. But what worries me is that we can see that the support structures, they're going somewhat um, a little bit of deformation. So since the support structures are very thin, so we might want to reconsider of how to design the support structures, because if the internal support structures break, that means my field lines, they're gonna be um, prone to catastrophic failure during uh, operating condition due to internal field pressure and external chamber pressure. So we looked into the 100 bar and 50 bar condition, and so we can see like there's a quite a bit of deformation going on into those internal structures at 100 bar condition. It's around 0.23 millimeter. When taking into the consideration of this internal structures dimensions, um, it is actually a little bit of uh, worrying that that much deformation is going on there, but especially on the smaller oxidizer inlets. On those one, the deformation is higher. Um, so based on this, we should be looking into for a remodification of the support structures and possibly reinforcing the support structures. Now, I'm talking now as I'm going through my presentation, I'm basically comparing it to the dimension. However, you might have question about the dimensions, but I do apologize that I cannot disclose you the dimensions for this injector. Let's look into the transient von Mises stress. So this is for around 25 bar pressure, so 2.5 megapascal. So for a 15-second test that we do during an operation, we could see that the maximum pressure went up to around 50 megapascal for a 2.5 megapascal input. The input is basically increased from zero point 0.1 megapascal to 2.5 megapascal step uh, periodically uh, during this 15-second period following experimental data pattern. So what we see if we compare it to the static structural design, structural simulation, we can see that the um, maximum stress that is actually lower than the results obtained with the static structural. That is due to during a static structural we were giving a constant 2.5 megapascal load pressure, which was basically worst case scenario. But during transient, it's not that we're increasing the pressure little by little at every single period. So that actually uh, gives you lower stress. Now during a 100 bar experiment, we can see as high as 200 megapascal of pressure, but still the pressures are the 200 megapascal of von Mises stress. Still, the von Mises stress is reasonably lower uh, if we compare it to the yielding stress, and we can make a decision that this injector design is okay based on pressure, based on stress. But if we look into total deformation on transient, we can see that it has a similar kind of deformation, not very high, um, but the internal structures they undergo similar kind of deformations as well uh, compared to the static structural ones. So we do need to actually look into reinforcing the structures, and we can also, even though those structures are also undergoing a very small amount of deformation time, we should still look into reinforcing those structures, because at 100 bar we were looking at like 0.2 millimeters of um, support structure deformation. So we should be actually reinforcing those support structures. Uh, Otherwise, the whole injector, the deformation along the fill uh, outer fill walls on the outer side are fine because that is experimentally observed um, during experimentation, and it internal can go up to a little bit around quite a few millimeter of deformation before basically plastically failing. So we can basically live with it, and but we need to actually look into closely with about support structures when we redesign it. So this is basically the table for the von Mises and the maximal principal stresses and deformations we encountered at different chamber pressures for our static structural simulation. And it seems that we go from around 35 megapascal to all the way to 222 megapascal. However, any of the stresses on here are not worrying for redesigning the injector, because most of these stresses are at stress concentration zones, and the median stresses are lower, way lower than the actual the maximum stress. So the yielding stress of 90 megapascal of Inconel is basically fine for this design, and we can basically actually go on with the same design and test up to 100 bar for structural conditions. Now let's look into the temperatures. Now for temperature, I've already said we've applied a heat flux onto the injector face. Now that injector face should have had an uniform heat flux and should have provided an uniform temperature distribution along the injector face, but it doesn't show that case, which is a little bit of it's kind of like which is a little odd, and I think we need to look more closely into the uh, input pattern. But you can see that the injector has the highest temperature at the injector face and the injector top face. So the faceplate is undergoing a very high heat conduction. We can also see that the thermocouple pores, they also heat up very fast. Um, Also, if you look into it, you can see that the field lines, the temperature on those lines are reasonably lower because I already uh, said that we're gonna be flowing fuels through there, and instead of convection we just gave a constant temperature because we have different fuels going in and different film temperatures, film coefficients occurring at different times. So that would be a little bit of complex for this simulation, uh, mm, and it'll be computationally expensive to do something like that on for this work. Now, if we look into the maximum firing input of 500 kilowatt, we can see that the injector face temperature went up to 947 degrees Celsius. That's really close to Incanon's melting temperature, and we should be yielding by that. Yielding at a very low pressure. I think for 500 kilowatt and 100 bar coupled, we should be yielding. So we need to look into a way to reduce the temperature on that injector face. The way, the best way is to implement a cooling line on that injector face. Now, for transient uh, conduction, we see the scenario becomes even worse because for transient, we're actually running it for 15 seconds at different heat flux is incrementally going up to 500 kilowatt of firing input. So that means we're heating up the injector very high, and you can see like now it is uniformly um, heating up on the injector face, and we've got about 1300 degrees Celsius of temperature on the faceplate. That is basically melting. Uh, that actually says the internal will start melting from the faceplate. So we need to actually look into cooling, and also if the temperature goes that high, our support structures will also start melting as well, and we'll have a catastrophic failure. To verify the temperature plots, what I did was I plotted a transient temperature plot at 100 bar, and I looked into the temperature patterns that we have from experimental results, and we figured out that they basically look almost similar. They have the similar pattern, except that on here the temperature, we already have the injector operation time, and on the experimental data we have the injector operation time including purging as well. So it shows a little bit of downward uh, temperature decreasing at the end, but for the for our case we should be having a temperature increment, and that's what we have, and we basically uh, have a reasonable um, comparison and a reasonable match between both data patterns. So that means our temperature is basically following closely to the experimental. So this is basically a summary of the results we got for different firing inputs and the temperatures, and we can see that up to 350 400 kilowatts we can go without cooling, but um, for 500 kilowatt of firing input we must need cooling as well. And even though the temperatures are lower at 350 400 kilowatt, I would still recommend to implement a cooling uh, so we do not have yielding due to long-term operation at those firing. So the design considerations that we need to make from these results is that we need to actually reinforce the support structures. We could actually do array of support structures inside the fill lines, and uh, or we could actually basically make the support structures thicker so they do not fail. Cooling channel needs to be implemented, and current design of the injector can withstand up to 100 bar of pressure without any uh, without any kind of strength modification for the structural loads. We should only look into reinforcing the support structures for structural loads. For conclusion, we have looked into uh, an FEM investigation of this additive manufactured injector at supercritical environment, that is high pressure and high temperature environment. The material we used was Inconel 718. We did a coupled static structural and thermal simulation and an uncoupled transient structural and thermal simulations. The structural simulations showed that we can go up to 100 bar of pressure and not fail, but however the internal support structures needs to be reinforced for this, should be reinforced for safety, and should be redesigned for operating at high pressure. The thermal simulations show that the highest temperature at the injector face, and we should be yielding due to those temperatures, and we need to implement a cooling design. So the final decision for this project is we need to basically redesign the injector to incorporate cooling, and while we're doing it we should reinforce the internal supports uh, inside the fill lines. These are the references that we looked into for this project. Thank you everyone for your uh, patient hearing. Um, if you want to contact me, you can contact me on my email at mislam12 at minors.youtube.edu. Thank you. Have a good day.